Let's try another example of solving for mechanical advantage of a lever, but this time let's use a second class lever.
So the rules for a second class lever is the fulcrum is on the outside, as is the effort force. So let's say the effort force is right here, Fe, and let's say we want that to be 10 pounds of force. We can't lift more than 10 pounds. And it's fighting this Fr, which is, let's say we're lifting up 50 pounds. Then let's say our distance effort, distance resistance, our distance to our force resistance, let's say that's 2 feet. And let's say we don't know our distance effort or our distance to our force effort. So we don't know this one, and we do know this. This is dr. I'll go ahead and label that. So my first question is, again, what is our mechanical advantage? And the second question is, what distance effort, what distance to our effort force will we need to get that mechanical advantage? So let's start with mechanical advantage, and of course we've got our two mechanical advantage equations. We've got AMA free, which is AMA equals FR over FE. And of course we've got I'm a deer, which is the ideal mechanical advantage, is the distance effort divided by the distance resistance. And so to solve for mechanical advantage, we need to find out what we have enough for to solve it, and we clearly have two forces, so we're going to use our AMA equation, AMA free, or the actual mechanical advantage equals force resistance divided by force effort, which we know the force resistance is 50 pounds. And we know the force effort is 10 pounds. And so that's pretty easy to solve. Our mechanical advantage is clearly 50 divided by 10. Well, that's just mechanical advantage of 5 because pounds cancel out.
And so hopefully that was pretty straightforward. But with that, we can solve for our dE by using our ideal effort force equation,
which says IMA equals AMA. So assuming that this is true,
we can then say
that d's are free, or dE over dr equals FR over FE. D's are free. And then, of course, we could just plug in our three numbers that we know and cross multiply and divide for the last one. But some of you might say, well, Mr. Anderson, do we have to go through all those steps? I know IMA, and I know the AMA, so therefore I know the IMA. I know that 3 equals 3. Since I already know the AMA, then I know the IMA is 3. So couldn't I just use this equation here that 3 equals the dE over dr, and we know dr is 2 feet? So couldn't I say that dE then, or couldn't we solve for dE this, or not? I don't know what I'm thinking. I don't know where I got 3 from. These are all obviously 5. And so let me take a second to go ahead and
fix this. So 5 equals 5, and the IMA is therefore 5.
Which means 5 equals dE, which we don't know, divided by our distance resistance, which we do know is 2 feet. Okay, and so, well, how do we solve for this? Well, we just multiply by 2 on both sides, and we get 10. We get dE has to equal 10, and then therefore feet. And then a cool little trick you could do here, whenever you have an equation like this, where you have a number equals a fraction, you can always put the number over 1. That doesn't change it. 5 over 1 is just 5. And then you can cross, multiply, and divide. You can do 5 times 2 divided by 1, which is, of course, 10. Just a cool little trick that you can keep in mind. But with that, let's go ahead and say what all this means. So again, work equals force times distance. So I'm trying to lift this 50 pounds. And to lift this 50 pounds a little bit, I need to lift my force effort a lot bit. So as you can see, it would go a lot farther. It would have to go a lot farther in order for this rigid bar to move that far. So I'm getting the same job done. I'm lifting this force resistance, but I'm going a further distance. So I'm having a disadvantage of distance by increasing it, making myself have to go farther. But in return, I'm lowering my force, which is my mechanical advantage in this system.